How do you pronounce your name? I'm sorry.
Marek, Sefranek.
Marek. Okay, so we're about to start what I believe is the last talk of this session. So we're going to have a talk about Plonk without random oracles by Marek. Thank you.
Hi, everyone. This is joint work with Georg Fuchsbauer. So there's this famous saying, all roads lead to Rome. And also in cryptography, especially in the context of the PHP transform, it often feels like all proofs lead to the ROM. So in this talk, we're going to find the one road that doesn't. And we will take the complementary approach to the previous talk, where we now want to prove security of Plonk without idealizing the hash function as a random oracle. So let me start by giving a few quick facts about Plonk. So this ZK snark was first introduced by Gapison, Williamson, and Chobotaro. It has constant side proofs, a little bit more than half a kilobyte, and sublinear verification time. It has a universal updatable setup and structured reference string, and it also supports custom gates and lookup arguments. And Plonk and variants of it are implemented in a variety of real-world applications. Some of them you can see on the slides. So we have these three properties, as explained in the previous talk: completeness, knowledge soundness, and zero knowledge. And usually for snarks, the hardest property to prove is knowledge soundness, which informally guarantees that whenever someone produces an accepting proof, we should be able, except with negligible probability, to extract a valid witness. So in the original work, they prove knowledge soundness of Plonk under the Q discrete logarithm assumption in the combined AGM plus ROM. So this assumption is a stronger version of the discrete logarithm assumption, where in a cyclic group, instead of just being given g to some random tau, we also get additional powers of tau in the exponent of the group, and then no adversary should be able to recover this value tau. And then this other model that's used here is the algebraic group model, which assumes or restricts attention to algebraic adversaries that behave in a way that whenever they get as input some group elements G1 up to GQ, and they output some new group element G bar, then they also need to be able to explain and provide a representation vector that explains G bar as a linear combination of all these previously seen group elements. Then this result by Lippmann et al., which was a previous result also about knowledge soundness, they managed to get rid of the AGM, and now they need slightly stronger but still falsifiable assumptions. They are variants of the Q-strong Diffie-Hellman assumption called the Q-ARSDH and the Q-split-RSDH assumption. So given this prior work, I think for the curious mind, it could already be enough to ask the question, can we prove security of Plonk without the random oracle model? But to better motivate why this is meaningful, let's consider a different motivation. So let's say we want to prove multiple statements in a succinct manner. So we're given these statements x1 up to xn, and then we want to prove their conjunction. And a naive way to do it is you could just run a snark on this combined statement and then get a single proof that proves all of them. But there's a big blow-up in this combined statement in the circuit size. So this results in very large parameters and long proving time, bad prover memory, and so on. And also there could be a different problem in this scenario where what if we only learn the next statement to be proved on the fly, so that we only learn some statements in an online fashion, which is, for example, the case in ZK rollups. So instead, what you would like to do is to use a recursive proof where you first just prove the first statement, then you compute a another snark proof that proves the second statement, and also the fact that you know a proof pi1 that verifies for the first statement. And then you apply this recursively until you arrive at this final proof pi(n) that testifies all of these statements. Yeah, and this technique enables many nice applications, such as incremental verifiable computation, proof carrying data, scalable rollups, and even succinct blockchains. So let's now unpack a little bit what happens in this recursion, especially if we are working in the RAM Oracle model. So what is the statement that we are proving in these recursive proofs we are performing, right? So we still prove that we know the witness for some statement, but in addition, we also have to prove that we now know another proof for which verification passes for the previous statement. So now if the original snark that we're using only has a security proof in the RAM Oracle model, we have the problem that if the snark uses a hash function and this model is RAM Oracle, in the statement that we are proving, this will be some fixed hash function. So now if you want to apply the security argument recursively to prove that this is still a knowledge sound or sound proof system, we run into the problem that the RAM Oracle is already a heuristic, and then essentially now we don't even prove that this is secure for the actual statements we will be proving about the hash functions, but we will then have to assume that there are some kind of RAM Oracle gates. So yeah, I think this is clearly a concern from a provable security point of view. And moreover, there's also this other result from the previous year, which we know many RAM Oracle uninstantiability results, but all of them use some contrived schemes. But this work, in this work, they actually show an attack on a version of a variant of the ZKProof protocol, which is a very natural protocol, and even variants of it are implemented in practice. And its security proof is in the RAM Oracle model, but they manage to essentially they show an attack where you can compute an accepting proof for a false statement, and importantly, these statements they need to involve evaluations of the hash function h, which is the case also for recursion. So I think with these two motivations, clearly we see it would be nice if we can have some soundness guarantees for some concrete hash function. So what we proved in this work is for knowledge soundness, we show that we now give a proof just in the AGM under the QD log assumption, and a new assumption I will talk more about later, the so-called zero testing assumption on some concrete hash function. So we avoid the ROM, and this new assumption is also a falsifiable assumption. And you see we still need some additional, we have this caveat of using the AGM, but due to the impossibility result by Gentry and Wicks, it seems very unlikely that we will be able to give a full standard model security proof by some reduction. Moreover, we show that both of these assumptions are necessary. I think I can maybe explain it for QD log because that's quite trivial. So essentially, breaking QD log corresponds to recovering the trapdoor of the parameters of Plonk, and then you can prove anything because there's a simulator for Plonk that can use this trapdoor to prove any statement, even false ones. All right, how about zero knowledge? So the previous work showed that in the RAM Oracle model, Plonk is statistically zero knowledge. What we did in this work is that we slightly relaxed the notion of zero knowledge to computational zero knowledge, but then are able to show it for a concrete hash function in the standard model, again under the same assumptions, QD log and the zero testing assumption. All right, let's come back to recursive proofs. So how does the AGM help us here? So there's no ROM involved anymore, which is nice. So the question is, right, if we get this proof pi2 in the AGM, we would then be able to extract the witness for the statement x2 and this other proof pi1. But what we would like to get is also the witness for the first statement x1. So how can we get it? There's this work recalling how the AGM works, there's this work by Lee and Seo where they extend the AGM. I will call it the recursive AGM for the purpose of this talk. And the extension is, think of the group maybe being an elliptic curve group. So group elements consist of 2 field elements. And what we now do is, we're not satisfied with just getting this representation vector C, but if any pair of field elements in this vector again lies on the elliptic curve, so it's another group element, then the adversary also has to explain this element recursively. And so on. So with this, we at least get a way to prove something about the real protocol in this recursive AGM. So I think it's an improvement over applying the random oracle model kind of twice. Yeah, and finally, I also want to point out that that Lee and Seo were the first to introduce a version of the zero testing assumption, which I will be talking about next. So let's take a look at this assumption. So we have some hash function that maps into some finite field. I'll first motivate it using some simplification, where I just consider a problem of you want to find some non-zero polynomial of bounded degree d, such that when you evaluate the hash function on this polynomial, it should be hard to find such a polynomial that this gives you a root of f. But this, unfortunately, is not expressive enough to prove any meaningful schemes secure. So we need something a bit more complex. So what we also need is not just the hash function, but there will be some commitment scheme that has some setup algorithm and a commitment algorithm over some message space M. And then we define this decoding function D that essentially we think of the message space as being somehow, so there's some interpretation of messages as polynomials. In the simplest case, you can think of M as just being the set of polynomials, then D is just the identity function. Maybe it's the coefficient representation, so then you have vectors that are mapped to polynomials, or you could even have vectors of polynomials, and then these polynomials are somehow combined into a single polynomial. So many things can happen with this decoding function. And the problem now will be we run the setup algorithm of the commitment scheme, and then the goal of the adversary is to find a message such that when you now consider a polynomial that corresponds to M, so you compute D of M and get some polynomial, we want that this is a non-zero polynomial, and we would like that when you commit to your message and then evaluate the hash function on this commitment, that this is a root of the polynomial. And this is the version that we use to prove security of Plonk. Let's maybe do 2 things. First, just for some intuition, why is there a commitment scheme? So in these PRP-based snarks that use Fiat-Shamir transform, essentially what you're hashing, right, is a concatenation of some commitments. So what we actually do for Plonk is we define the commitment scheme, which is KZG. We define an extension to like vectors of polynomials. So we just have like multiple committed polynomials in a vector. This will be like the abstract commitment we then hash. Okay, so what the adversary does, it gets the parameters of the commitment scheme and should return some message, such that decoding this message gives us this univariate polynomial f. And then also in our case, the commitment scheme will be deterministic. So then when you commit to it, you always get the same value, you hash it, and then you get this in the protocol. This would maybe be a challenge in one of the rounds, alpha. And if alpha is the root of f, then you break the assumption. All right, let's consider a toy protocol and see how we can use it. So let's say we have a prover that claims he knows 2 polynomials, f1 and f2, such that f2 is equivalent to the cube of f1. So one standard approach to do this is to use the Schwarz-Zippel lemma and let the verifier send a random evaluation point and then just check this polynomial identity at this evaluation point alpha. So the way it then works is we use some polynomial commitment scheme. We commit to our 2 polynomials as the first message. Then we receive back this evaluation challenge alpha. We send the 2 evaluations and also these 2 opening proofs to the verifier, who then checks these opening proofs and also checks that the evaluations, so that y2 equals the cube of y1, and accepts if all of these checks pass. Then one can apply the Fiat-Shamir transform. So here I'm ignoring any parameters. You can also include them. Just for simplicity, I only hash the first 2 prover messages to derive the challenge locally. All right. And now I want to show you how we can define a variant of the ZT assumption to prove that this approach is sound. So for this, we will essentially assume that the polynomial commitment scheme is secure. I will not define this precisely, but there's some form of evaluation binding and so on. So the claim will be if we define this function d that takes 2 polynomials as input and defines a new polynomial as f2 minus f1 cube, then if we get an like successful malicious prover, which essentially produces a proof where the 2 polynomials it committed to don't satisfy this identity, then what we can do, we can now define a reduction that's trying to break this ZT assumption. It defines the message, so it gets the parameters, it gives them to the adversary, and then it defines its message as just these 2 polynomials. Then when we evaluate the function d, clearly we would get a non-zero polynomial here because, again, this statement is false. Then the verification check at the end, right, corresponds to evaluating these 2 polynomials at alpha. So we get, if this passes, we get that alpha as a root of the polynomial. So we break the ZT assumption. Of course, you might be asking, how can our reduction define M? So for this, we need to extract something. So for example, if it's a KZG polynomial commitment scheme, it is extractable in the EGM, and then we can essentially extract these 2 polynomials from the 2 commitments. All right, so I will not actually open the box of Plonk for the sake of this talk, and this toy example is quite simple, so I will point out a few challenges or differences in Plonk. So the main difference is, right, it will be a multi-challenge protocol, and handling these is not as straightforward as here. And also the first round of Plonk, you actually get 2 challenges simultaneously, which required us to define a multivariate variant of the ZT assumption, but we also show that this variant cannot be any easier than some specific univariate variant of ZT. Okay, so what we also do in the paper is to try to give some justification for hardness of this ZT assumption. So, first, now I guess it's true that all roads lead to Rome. So we now model H as a random oracle, but take a real commitment scheme. And if we assume that it's binding, we can show that for any function d, we get that it satisfies, or that the hash function together with the commitment scheme satisfy the ZT assumption. But then we also want to prove it for a concrete hash function, and what we do is we take the KZG polynomial commitment scheme, and if we analyze it over a generic group, so idealize the group, then it just suffices for the hash function to be balanced, which just means that if you essentially that it preserves min entropy. So if you like take some random values and hash them roughly, the output should also be random. This is a weaker assumption than collision resistance, but we also show that this is implied by collision resistance, so maybe a more standard property that you can assume for your hash function. All right, to summarize the results, I just want to give you a quick overview of the security landscape of Plonk. So let this be the plane of all BPT adversaries. So if we take the previous results, we get that for all of these adversaries we have knowledge soundness, but this is a heuristic argument. So we only know that this holds for the random oracle, but for any concrete hash function, we again hope, or also for many schemes we have not found any attacks. So we have some confidence, but it's not an unconditional security guarantee. And what our work essentially adds on top of this is that for now a restricted class of adversaries, we actually get a security proof without any heuristic arguments. So we know that for all adversaries that essentially only compute group elements by linearly combining them, we really can take these 2 assumptions, and if the hash function satisfies the ZT property we define in our paper, then we really get null soundness even in the standard model. Of course, one might be curious what happens outside of this class of algebraic adversaries. So there are, for example, some adversaries that do so-called oblivious sampling, where you derive some group elements in a way that you actually don't know the relation with respect to your input group elements. And there are some attacks against some simpler sub-protocols, also used in Plonk, but we don't know any such attacks on Plonk. And I think with the security proof by Liebma et al., it would also be surprising if you found such an attack, because we have a security proof in the ROM, so this attack should clearly not work against the ROM, so it must work for some concrete hash function, but that would already be very surprising if it somehow depends on the hash function to construct such an attack. All right. Let me conclude the talk by, again, recalling the Gentry-Wicks impossibility result, which essentially makes it implausible for us to obtain a full security proof of a snark such as Plonk in the standard model. So from my point of view, the best we can hope for is if we can prove security into kind of independent and separate idealized models. Essentially, we get the best we can hope for. So now we have a proof that idealized the hash function, or we take a real hash function, but then idealize the adversary or restrict the class of adversaries. So I think this is a nice property to have for a scheme. Let me close out my talk with some open problems. So clearly motivated by the previous talk, can we maybe lift our results and also obtain simulation extractability without the RAM Oracle model? This actually seems quite challenging because we don't have. So I think in this prior Liebma's work, you actually rely on the RAM Oracle for the simulator to be able to simulate things without this trapdoor, but this we couldn't do in this model, so it will be quite challenging. Another thing, of course, is can we actually instantiate a hash function, like find a commitment scheme and a hash function and instantiate this property, this CT property in a standard model. Also, we need some more crypt analysis for hash functions that are being used, because we also show that the CT property we define, if you can break it, then you can also forge proofs potentially on Plonk for like Plonk. So it would be interesting what happens when you plug in, I don't know, SHA-3 or Poseidon into Plonk, and what happens with the again the functions that we define in our paper. And finally, since one motivation was recursive proofs, I think that the recursive AGM stands on, or like at least it gives you a full proof. But the question is, how strong is this model? Too strong? So it would be nice to study this recursive AGM and scrutinize it. All right, that's it.
Do we have any questions?
Hi. I have a question about this problem of instantiating this zero testing. So, like, because you were saying it's a sort of correlation interruptibility property. So why can't we use, for instance, functions that are already correlation interruptible for all sparse relations?
So actually, it's not directly. I don't know how to say it. Like, there is actually a way to cast this as a form of correlation intractability, and we show actually in the paper that you can instantiate it using correlation intractability. The problem is that then this commitment scheme needs to be a correlation intractable hash function, so it doesn't work for KZG, right? And the problem is these correlation intractable hash functions. We want these additive homomorphic properties from the commitment scheme or some other special properties, right? And it seems like these correlation intractable hash functions don't have them. So I think it's still a big challenge to take a commitment scheme that's useful for building a snark and then actually focus on this outer layer, the hash function that's evaluated when you do the Fiat-Shamir, and try to find something there that... like one problem also maybe to say it in correlation intractability, you need these sparse relations, and when you have these compressing commitments to these polynomials, there's a few problems there. It's not straightforward.
Thank you.
Okay.
Hello. So I understand this CT assumption is more like a family of assumptions instead of just one assumption.
Yes, so it will be a concrete function D that you have to specify how it maps the method space to polynomials. And in our case, it really depends on Plonk. It's quite a specific structure we get.
Right. So my question is, let's imagine you have Plonk running in production and you've proven this assumption. So let me rephrase the question. So you've proved this assumption for KCG plus this unbalanced property of the hash?
Yeah, or think of it as collision resistance maybe.
Does your proof extend to any or to many different versions of this CT assumption?
Yes, so in these two proofs, again, we use some idealized model. So I think that's a bit of the caveat with these results, but we prove it for any D.
Okay. And does your proof rely on the fact that you're hashing, you represent points with two coordinates? Well, what if you only represent points with one coordinate and one bit of the other coordinate?
I mean, right, so these group elements, like you can still interpret this, so then you would probably change this recursive AGM and like you might even then consider each single entry. I don't know, I guess it's a good question, like how one would define it, because you just need a single bit, which you don't have, so you don't necessarily have single bits in the representation. But I guess you could just try both bits maybe and say, if any field element with either of these two bits gives me something on the curve. Yeah.
Okay, thanks.
Thanks for the talk. So can you explain a bit how much this your result actually depends on the Plonk, and what properties of Plonk do you need for it to work, and how much is it generalizable?
Yeah, so I think one thing I forgot to mention is that the security proofs becomes quite modular in the sense that we really focus on each round, which is kind of nice. We essentially kind of define a different function D for each challenge round. It still overall will just be single function D, right? Because these rounds take different inputs to the hash function, so you essentially can do a domain separation when you define the D. And these Ds really depend on Plonk. Like, let me try to recall, because these functions are very long, if I can give you an example of this. Like, for example, when you use this optimization of Plonk where the verifier doesn't use the local random challenge, right, to do the fetching, but derives it also using the hash function. For this, we essentially can define a function D which has a root. This polynomial that gets out of there has a root exactly when the batching essentially, right? So you want to verify two things, and then you use a random challenge, right? And let's say one of these doesn't hold, then there's some probability that the prover is lucky with the challenge and the batching proof still verifies. And there's like a corresponding function D you can define that essentially if the prover can find such a transcript that gives you, I mean, actually the prover is not finding, or the ZT adversary is not trying to find the transcript, it tries to find the polynomials that are then committed to a transcript. Yeah, when you find this, you can then fool a verifier. Yeah. But yeah, it gets more complex, especially with the permutation argument. That's probably the hardest part of the proof.
So if you take another SNARK, then you have to basically redo it, or?
Yes, so I hope to essentially extend this to maybe get some more general result for like we try to identify some properties of Plonk that we needed essentially for the proof, and then maybe have some more general statement about class of, I don't know, PLP-based protocols.
What about GKR?
Yeah, so I'm not an expert in GKR. I haven't like really spent much time thinking about it, but I guess it would be, I think what this should mean is probably that we can't, I don't know, I think my intuition is, so I think also another thing I forgot to stress is that the attack on GKR is algebraic, so we kind of protect against it. So it seems like now to break Plonk, at least with an algebraic adversary, you would really have to break these functions D that we define for the hash function. So yeah, my intuition is for GKR, you probably just can't get a security proof under this assumption. there must be some problem. But it's interesting. I just haven't had the time. I would actually like to look into it, open the full GKR protocol and see what happens when you try to apply this assumption there.
Okay, so as a concluding remark, I must say, so this is a very interesting work, and please confirm. So to have confidence in the zero testing assumption, we need to have confidence in the zero testing assumption as applicable to a triple D commitment scheme hash function. Is that correct?
Can you say it again?
Yes, so the zero testing assumption is an assumption about triple hash commitment D. Yeah. Is that correct?
Yes, so for Plonk, I like to kind of just talk of it as a property of the hash function, just because I'm assuming I'm instantiating with KZG, so KZG is kind of fixed. But in a general case, you really have a pair. It could be any commitment scheme and any hash function, and then it's a property of their composition.
Right, so I guess in order to say have confidence of this, we should find a broad class of Ds and a com and a hash that seem reasonable and popular for which this might hold. Conversely, to see if this, to sanity check this and see if there are impossibilities and such, one could say, here's a commitment scheme for which no hash function is going to make it work for certain interesting classes of D, or here's a hash function for which no commitment scheme. Yeah, so if anybody has ideas on this, please.
Yeah, I think
but this is a very interesting work.
A lot of space to be explored. I didn't have time. All these things are interesting, but it's just too much for one person, so please take a look.
Yeah, let's name the speaker again. There's going to be a break now, and we'll resume at 4. Thank you.